this video, we're going to talk about the exam style questions linked with chirality, which is the second video in this series on chirality. We're going to go through the very familiar questions, and remember those questions are very formulaic when it comes to chirality. They just change the examples in, so if you practice enough, you will be fine. So first of all, though, we need to talk about identifying the chiral centres. Now, the chiral centres have 4 different groups attached to them, and they must be of carbon when it comes to organics. So a carbon centre with 4 different groups attached to it. So to identify the chiral centres, you have to look at the different groups. Now, our exam tip for this, and we'll use this as an example, is for simple molecules, draw the molecules out as displayed formula, and which we've done here. Look for the carbon atoms with 4 different groups, and if you're looking over here, you can see that this is the chiral atom, the chiral carbon, because it has the CH3, which is different to the NH2, which is different to the H, which is different to the COOH. An important thing to notice is that if a carbon has a double bond, it will not be chiral, because it can't have 4 groups. If it can't have 4 groups, it can't be chiral, which is what a double bond does. It makes it have only 3 groups attached to it. So it's a good tip, if it's a double bond, don't consider it a chiral carbon. And the last thing we're going to do is look at the effect of symmetry down a molecule when you have a ring. And we'll do that in the next example. But for now, here is your chiral centre, because it's connected to these 4 different groups. Now let's look at something a little bit more complicated. So as you can see, I've already drawn a plane of symmetry down here to try and help. It's just this faint red line here. So if you look across, I can look already, there are double bonds here, here, and here. So I can discount it from what I previously said. If it's got a double bond, I'm going to discount it. Now it will be presented to you in exams as skeletal formula because that's more complicated. So there's 2 tips here. One is a double bond, just discount the carbons, they're not chiral centres if they've got a double bond. The other one is if there's 2 bonds going to the carbon and nothing else on it, just 2 bonds like this and nothing else, then it must have 2 hydrogens coming off because carbon has 4 bonds and we don't draw the hydrogens in skeletal formula. So therefore that is definitely not chiral because it has 2 hydrogens on it and 2 carbon groups. The 2 hydrogens mean that it doesn't have 4 different groups as done in our rule there. Then we look at this one and we can see that that carbon, okay, is connected to this big group here and it's connected to this oxygen and connected to this carbon. Now the plane of symmetry down the middle here just helps you identify the top half and the bottom half because you're going to compare the top and bottom half to know whether they are different groups. So I can see that that top half looks very different to that bottom half because of this plane of symmetry. Therefore, they're considered as 2 different groups, and therefore I have my first chiral centre here. I then move over to this one here. And again, another tip, investigate the atom, the chiral carbon, if you see 3 bonds coming off it. See 3 bonds coming off it, check that those groups are all different. So if we look here, plane of symmetry is down the bottom here, and you can see big group coming off. We don't really need the plane of symmetry on this one because this big group comes off here. You've got the CH3 that's coming off here and this big kind of nitrogen containing ring here. So therefore that's definitely 4 different groups coming off here because there's a hydrogen coming off as well, and that's your second chiral centre. So this one has 2 chiral centres in it, and the name for that is diastereoisomer. We'll talk about that a little bit later. Now let's go on to the most common exam question, and that's what's the number of chiral centres in a molecule? They'll just change the molecule. This is the same question over and over again. They'll just change the molecule. So they give you your different options for how many chiral centres there may be, and they give you a very large molecule like this. And let's go through that and how you would do that. If you want to go off on your own and do this yourself, have a go before I explain the answer. Let's move the question over and let's start looking at it. And we're going to do this using lines of symmetry, looking for these chiral centres, 4 different groups. Now, tips in the last part of the video were if they're double bonded, they can only have 3 groups to them, so therefore you can just discount them. So there's double bonds here, double bonds here. Okay, so we can skip all of that part. Then our other tip is if there's 2 bonds to it, it must have 2 hydrogens, so therefore that can't have 2 can't have 4 different groups because it's got 2 hydrogens coming off it. So therefore that can't be chiral either. This is not chiral and this is not chiral. And we're looking for carbons that have 3 bonds coming off them. So here's our first one here. So let's put a plane of symmetry down. And that allows us to look at the different halves of the molecules. So we've got this half of the molecule and this half of the molecule, totally different. And then we've got an N coming up here. And it's very common that if there's three bonds coming off a carbon, if the halves are different, then generally it's a chiral center. So if we look here, 3 different groups, and there is a hydrogen coming off, so therefore 4 different groups in total, and therefore we have a chiral center. Now let's get rid of that line of symmetry and carry on down the molecule. So as we carry on down the molecule, we've got again 2 bonds, 2 bonds. Because there's 2 bonds to each one of those carbons, there's 2 hydrogens coming off each one, therefore not 4 different groups. And then we come to these 2 carbons here. So those 2 carbons will require us to put on a line of symmetry again, and you could do this in pencil as you're going along. Okay, and if we look again at the halves, we can see the halves are completely different. So we're going to do the bottom one first. You can see this half is completely different to this half. Okay, and then you can also see that as you go up, it's a different top. So if you look here, the top of here looks very different to the side of here, okay, and to this side. So therefore 3 different groups and an extra hydrogen. So therefore we have a chiral center. We then look at the top one. That does not look like that, okay, which does not look like this. Okay, and all you have to do is look along 2 or 3 carbons, you can see that they're totally different. Now that means we have another chiral center at the top. We then continue round and we've got 2 bonds again, which means 2 hydrogens, which means not a chiral center. And then we come to our 3 bonded carbons here, 3 bonded carbons here. So that means we need to get rid of our line of symmetry and put another one in, and we're going to do this bottom one here. So again, on the left, you can see it's very different to the right, which is different to this ester that you've got on the bottom. And it's got a hydrogen coming up, so therefore another chiral center. Get rid of our line of symmetry, and then we look at this carbon right here, put another line of symmetry in again, looking at the top half, looking at the bottom half, they look very different, and then the OH is very different as well, and there's a H coming off, so 4 different groups again. So we have now got 5 different groups, 5 different chiral centers, 1, 2, 3, 4, 5, and hence our answer is 5. And that is very, very common, so make sure you practice it in the worksheet that's attached and throughout the video. We're now going to go on to do the next most common example, which is identifying how many stereoisomers. And they normally give you this related to structural formula. So you've got your structural formula right here, and that makes it a little bit more difficult. They'll then give you options of how many stereoisomers you have, okay? And then you just have to go through that molecule. And I'm going to show you a simple method to find out. So let's move this over to the side, and let's start going through that simple method. So step 1 with that simple method is going to be, you are going to draw the molecule. Now you can draw it in displayed if you'd like, but I'm going to draw it in skeletal. So all I do is I track along from the CH3. So the CH3 is starting here. There's my CH3. Then it's bonded to CH. That CH is then bonded to a double bond. So we've got to this point here, and that's the carbon there. We'll then go to another carbon. Okay, and that carbon there has got a Br on it. Okay, so the Br is now then on there. We've got a CH2 to a CH. So here's a CH2, and there's my CH. And then from the CH, I've got a double bond. So there you have your molecule. So we've got our molecule, and then it says how many stereoisomers are there. So what you've got to do is look at it and go, well, where can I see stereoisomerism? So stereoisomerism, okay, is related to 2 different areas. So we can either have EZ, okay, or we can have our optical isomers, which we discussed in the first video. So EZ or optical. So we're going to look in here and see whether we've got EZ or not, and see whether we can find it. So here I can see that there's a double bond, and I can see that there is a carbon coming off here. There's another large group coming off here. Okay, so this essentially has got two hydrogens coming off it. So I could call it cis-trans, or I could call it EZ if I'd like. Okay, and I can see from this, if you're being really good, you can see if I twist that and just look at it from that direction, I can see the different groups coming off it. So let's, just to make it really clear, let's put the hydrogen on here and put the hydrogen on here. So we've put the two hydrogens on, and we can then prioritise. So if you haven't done this before, use the yellow. Okay, you can say that. Let's prioritise the groups and just say, right, okay, the highest priority group is going to be the one with the highest proton number. So carbon has a higher proton number than hydrogen, and therefore the highest priority group here is that group. And then we look at this side, we say carbon has a higher priority than hydrogen because it has a higher proton number. So that is number one here. So that means our high priority sides in this molecule, our highest priority groups are on different sides. And if they're on different sides, if you remember, it is going to be an E. So this one that I've drawn is an E isomer. But not so important for this question, but good revision nonetheless. We then go to this carbon right here. So that carbon right here has three different groups coming off it, plus a hydrogen coming off it. Therefore, that is chiral, and often chiral centres are labelled with a star. Okay, so that is your chiral centre. We then go to the double bond here, and this is the mistake they are wanting you to make, is that has two hydrogens coming off. It doesn't have these two different groups here. Okay, it has two hydrogens of the same group, so therefore there's no E or Z on there at all. There's no ability to have a stereo isomer. So that means we have two different parts, and this is the clever bit. So the clever bit is to say, how can I find all of these isomers without actually drawing it? And you can do it without drawing it. So all we have to do is say, right, we know, let's do our first isomer. We know on the first isomer, let's just pretend we've got, we can do E, which of course we have here, but we can do E, and that's going to be our alkene. Okay, and then we've got our optical isomer here. And this is why it's quite useful to be able to label optical isomers. It doesn't matter whether you're correct whether it's R or S, it's just a label. So we're going to say, well, we could have the R with the E. And then we could have another E, and then we could have the S with the E. Then we have number 3, and we could have the Z. The Z can go with the R. And the fourth, the Z, can go with the S. Now that means that for that molecule, without drawing all the different isomers, if I just know what the labels can be, E or Z, R or S, I can count very quickly, 1, 2, 3, 4, and that means there are 4 different stereoisomers that can be made of this molecule. Well worth practicing this type of question, and well worth going through it. Very, very common. So we're moving on to our last question on diastereoisomers. It's one of my favourite questions because it looks really complicated, but if I teach it properly, you learn it properly, it's actually a very simple process you can follow to get this right every time. So a molecule that has more than one chiral centre is a diastereoisomer. Don't worry about the word diastereoisomer, you don't need to know it, but it does help just to give it a label. So more than one chiral centre in the molecule, diastereoisomer. Now we're giving you a molecule called isoleucine. So this is an alpha amino acid, and here is your R group coming off. That R group is how they try and introduce more chiral centres. So if I show you the two chiral centres, hopefully you can see this is a chiral centre and this is a chiral centre. Which means you've got two chiral centres, therefore a diastereoisomer. And the question looks like this. Can you draw all the stereoisomers of isoleucine? So here's isoleucine, as we had in our previous slide, and just think about it. In the previous, we can label these as R or S. So it can be the R or S, depending on whether they rotate the plane of polarized light. it doesn't matter whether you label them properly or draw them exactly, as in the draw the R1, draw the S1. It just matters you draw all the stereoisomers. So you don't, but it's much easier to label them to do that. So they can exist as RR, so R, 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 S, 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 R. Okay, which means 4 different molecules. Now you draw them like this. So if we put it down to the side and then we put our labels back up again, RR, RS, SR, SS and SR. So what we do is we take our pen and just start drawing them out and identifying the different chiral centers. And there's an easy way of doing it. The easy way is to go, look, here is the 2 carbons. So it's 2 carbons. If I go down here, that is that carbon there and that carbon there. You choose the 2 chiral centers. They'll almost always be right next to each other. And then what you can do is draw your bonds, okay, and draw your dash and wedge. There's your dash and wedge. And that is how you do it quickly and easily. It can become very confusing. So you take your 2 chiral centers, which are almost always going to be right next to each other, and you draw your dash and wedge. You've got 4 bonds coming from them, 1, 2, 3, 4, and there you go. And then all you do is start putting the groups on. So I'm going to do the first one, and you can see from the first one here, hopefully you can draw it before me, and you can see there is a hydrogen coming off it, which we're not showing, there's a methyl coming off it, which we're not showing, and then there's an ethyl coming off it, which here, and you can see this big group right here. And the big group coming off is this carbon here, so I don't need to worry about it. The big group coming off, this is our CH3. This one is going to be our ethyl group, so CH3, CH2. That bit there, CH3, CH2. Okay, and then we haven't drawn our H. So there's our H. So we've drawn this side here. So the methyl, the ethyl, and then that carbon is that carbon there. Okay, and we've drawn a hydrogen as well. Now we need to move on to this one. And we can see it's got COOH and an NH2. So let's draw COOH and NH2, and then draw a hydrogen. And that is all we do. So then what we do is we label that as R, and we label the other one as R as well. Again, it doesn't matter whether they are R or not, it just matters we've labelled them with something. Okay, and then all we do is we use our method that we had before, really simple method. We redraw that again, and then we put the ones in the plane, we put them back on normally. Okay, and then we do our dash, and then we do our wedge, and there we go. And all we do is we label what we want them to be. So we've got RR, let's do RS now. So that's going to be R and S. Remember, if we're going to change from R to S, all we do is swap the groups around. Okay, and there you go. I'll swap the group rounds. I'm going to do R. So I'm just going to copy this over. Okay, so I've just copied it over. So I've done RS. So let's go over to here and start doing, because we've done RR, and that is all done. Okay, and we've done RS. We're now going to do SS. So we start again, we put our carbons right next to each other, we put our dash and wedge. Okay, there we go. There's our wedge, there's our dash. Okay, and we do it again. And then this time we're doing SS. So that's R. Okay, so I need to swap the 2 groups around. So H this time is going to be at the bottom, and then the CH3, CH2 is going to be up there. Okay, and then we go to this other side here, and we say, right, okay, I'm doing SS. Okay, where's the S? Oh, the S is down there. So I can just copy this over. So there's NH2 and COOH. Okay, so I'm just copying it over. And again, just copy the 2 top bits over. So we have done RR, RS, SS. And that means underneath we have done our SS. And we're just ticking them off. We'll now go to SR. Again, wedges and dashes. And you get quite quick at these once you start doing them. And this time we are doing the SR. Okay, so we're doing the SR, so S and R. Let's go across again and we can see here, where is my S? My S is up here, that is a CH3, CH2, and an H. Copy the two top bits over again. And then I want an R, that's an S, I don't want that one, I want an R is up here. That means the CH2, COOH goes at the top, and the NH2 goes at the bottom. And what you've done here is you've drawn every single molecule that has all the different types of optical isomers in there. It's 4 different types. So once you analyse the 4 different types, RR, RS, SS, SR, you then can just say copy them from one to the other, and that's it. So the advantage of just putting a label on means that you won't miss any out. If you try and do this by mirror images, it's so hard. Okay? Do it this way. It's simple, it's easy, it's effective, and it means you'll never get this question wrong, ever. So in the past 2 videos, we have gone over optical isomers, how to draw them, how to recognise them in lots of different complex examples, and you've hopefully gone over these exam questions. Now's time to go and look at the worksheet and practice all of those skills, because these questions, remember, these questions are very, very formulaic. Okay, so if you get used to doing different ones, you'll do extremely well in your exams.